Hello world, thank you for your interest. My name is Haiko Lietz. This talk is about social network analysis with digital behavioral data. And this talk here is accompanied by a paper that is about to be published in the GESIS Easy Social Sciences journal, and that paper is available in German and in English. And what we will do today is that for those of you not familiar with network analysis, we'll shortly go into the history and philosophy, then come to talk about this new digital behavioral data that we have before we move on to application scenarios or the things or good things we can do with that data. And finally, we'll close with some challenges. So starting with what is network analysis, this goes back to the 20th century, the early 20th century, to Moreno, who was one of the first to really not do this metaphorically, but analytically. And what we can see here is a network of football players and how they like or dislike each other. So networks in general consist of nodes and edges, and the nodes are here, the dots, and it can be persons, but we will see can be many other things. There are two typical levels of analysis. One is the micro level or the node level, where people are typically interested in, the properties of the nodes. And this can be, for example, here in this example, simply counting the number of edges that a node has. So there's an imbalance there. Few have many edges and many have few edges typically. Then there's also the macro or the graph level of analysis, where like the whole graph is taken into account, for example, as in this example here, to divide the nodes into two clusters by whatever metric, there are many of those. And some key insights in social network analysis have been that that social networks very often consist of groups, the ones we have highlighted here, and very often those groups are homogeneous. This is the property of homophily, that nodes very often connect to similar others that are similar in some attribute, for example. Then there's this finding of structural holes. So groups are often separated by structural holes. That is, there are not many ties between groups, not many edges between groups. And since there is this homophily or homogeneity, ties that bridge structural holes are very often sources of novelty. So we have covered a few basic concepts that we will revisit during the talk. Now, we have talked about networks where the nodes are persons or groups or entities with agency in general, but nodes can also be words, for example. Then we would have one type of semantic network. And this kind of research emerged in the 80s. So in this case here, you have words that are often used together. This is then the edge. And then in the 90s, there was the cultural turn, which focused on the combined analysis of social networks and semantic networks, where the nodes can be symbols, words or references, something like that, something without agency. And that is a good thing because it gives us an approach, a way to study culture. And the two things really go together. You learn much more if you study the two things together. Now regarding the philosophy of network analysis, it typically builds on full samples, on complete data where you want to have and often have like all relations among a set of nodes, or like all nodes that belong to your system of study. And this field moves away from the person as the prime unit of analysis, a unit of observation, and relations become the unit of observation. Actually, those relations are transactions, stepping away from the notion of self-actions that is often connected to the behavior of rationally behaving persons, and also moving away from the interaction term, which is often used in you know, a variable-centered approach where you have interactions of variables. So in general, like the social sciences, even though there's a lot of social network analysis being done now, it is still very much focused on the person as the central unit of observation and sample-based approaches. And now there comes Duncan Watts, who you see here, who 10 years ago says, we have finally found our telescope in the social sciences, referring to the situation in astronomy many centuries ago, where the telescope really brought a revolution and a breakthrough in terms of research and insight. So what is this new telescope of the social sciences? It is not just, but definitely digital behavioral data, new kinds of data, but also the hardware and the software to analyze it. The two wouldn't make sense without the other. One would not make sense without the other. And key point is that this data exemplifies transactions. They are records of transactions as we have introduced them in the beginning. And like to put some flesh to that concept of transactions, let's use a tweet as an example of a transaction. In this case, it's a tweet by Duncan Watts. And the first dimension that a tweet or a transaction in general can have is a social, the aspect of a social relation. In this case, we see here that, of course, Duncan Watts is the sender of this piece of communication, but there are three people mentioned in the tweet. So you could construct a network of @mentions, you know, who mentions whom if you had many tweets. But we also know that he has like many followers, and he also follows some people. So you could also create a much bigger and much denser follower network. Then another dimension of transactions is the communicative content, which you have. In this case, it's the tweet content. And like a special case of content could be a hashtag, which can be easily extracted and studied. Another dimension of transactions, sometimes not part of the transaction, but in this case can be easily added, is attributes and attitudes of the sender. So here we have Duncan Watts's profile, Twitter profile, and we see that, for example, he lives in New York and he is a university professor. And finally, this kind of data is timestamped. And here, this tweet was from March 11, but when you download the data, you will also get the seconds of that day when that tweet was sent. So in sum, there are those 4 dimensions of transactions, and you have them to a varying extent, depending on the data set you have. Now moving to definition of digital behavioral data, DBD. DBD are traces of behavior left by the users of digital technology, or in another case, traces harnessed by digital technology. And we'll go into 3 different types. First type, where the traces are left by the users of technology. This is called found data. We have come to refer to it as found data. And the first distinction is, in the cases where the action is also its technically facilitated observation, this is the first type. And the example is Twitter, because the tweet is actually like an operation in the technical system. And in this case, you have all four dimensions of digital behavioral data, as we saw. Now, in the second case, where the action is not its technically facilitated observation, an example is email, for example. A telephone call would be another example, where it's more easy to understand that the call is not its technically facilitated observation, as in the case of a tweet, but we'll later use the example of an email, where the attributes are not part of the email, but can be added to an email, as we later see. Data can be enriched. So the third type is where the trace is not left by the use of technology, but is harnessed by digital technology. This is then designed data or digitized life. And one example is people wearing a socio-metric badge, which is an electronic sensor that people wear, which detects who is close by. And then you can construct face-to-face interaction networks, better called transaction networks would be more, would be better. But other examples are like using your smartphone to, for example, count the number of steps you have made. So that would be another example for digitized life. So the three types we have exemplified with Twitter, email, and sociopatterns are now in relation to the 4 dimensions of transactions in a table. This is not like a law that type 2 always has communicative content, but it's the examples we use here. And it is helpful to think about the application scenarios that we will talk about. The first scenario will be socio-semantic analysis, where we make use of the combination of the social relations and the communicative content. And the second application scenario will be about mechanistic modeling, in this case, only using like social relations and the time information, which is needed if we want to think about mechanisms. But before we go into the first scenario, it is helpful to think about patterns. What are patterns? The regularities in the macro behavior or in the macro state of a system or a network. One example is the existence of groups of actors. In this case here, it's a Twitter data set, and we see that there are groups here tightly connected within and not so much to others. So indeed, there are those structural holes here, right? And the color in this example is party affiliation, because the nodes are politicians, and this is a follower network. So there's much homophily, because usually people from one party follow each other, or politicians from one party follow each other to know what, you know, people in their own party they talk about. Another example would be of a pattern. Example of a pattern would be the existence of a structured discourse. In this case, we see the hashtags that were used by the politicians already. This was 2013. It's an old data set, but interesting one. And we see, for example, the colors here signal different topics. So blue is a topic back then. This was the surveillance NSA scandal. And now going to the application scenario 1. The network we see, so like most typically studied, social network nodes are persons. And we've talked about this network. On the other side, we have this information on which tweet uses which hashtag, formally which artifacts are used in which transaction. But what we can do with it is we can create this semantic network, which hashtag is co-used with which other hashtag in, you know, all of the tweets we have. So we have the two kinds of networks, and we can, to start doing a socio-semantic analysis, we can map the information of the topic, or in other words, the color. We can map the topic or color back onto the social relations. For example, we see that the Pirate Party back then was more or less the only one that talked about the surveillance scandal. So this gives us, you know, is one way to reap benefits from the rich data that we have, doing something that's very interesting, doing a sociocultural, socio-semantic analysis. And here we see that actors are just one entity among others. Words, symbols are the other ones. Transactions are the unit of observation, taking that really serious. And if you're interested in this kind of research, there's good work published in the Poetics Journal, those special issues referenced here. Now moving over to the second application scenario, let's think about patterns in terms of different models of behavior. If we have an individualistic model, then the understanding would be that patterns emerge or arise from transactions. This would be, for example, the kind of thinking you encounter in methodological individualism. For example, rational choice, where you have actors, having free will and behaving rationally according to their internal mental models, not taking into account the network structure. And Mark Granovetter has nicely characterized this as an under-socialized conception of human action, because network structure does not influence this, this behavior. Now, in a functionalistic model of behavior, patterns would influence transactions. This is the notion of downward causation. So they have an effect on transactions. Patterns have an effect on transactions, meaning they influence transactions. And you have, for example, in the past century, Parsons' theory was very famous and widely practiced, which is the idea that norms very much influence human behavior, up to the point where they are like a straitjacket, where people don't have degrees of freedom to behave differently. And Granovetter has characterized this as an over-socialized conception of human action. But of course, the two things can go together, right? And if this happens, then those are typically feedback models of behavior, analytical models, where patterns arise from transactions, but also at a later point, and this is important, influence transactions. We have in the beginning talked about structural holes and people that, if they bridge structural holes, that can have benefits for them. And those are actually analytical models of behavior, because what they require is that the agents in the network observe the network. They observe there's a structural hole, and as in Bird's case of brokerage and reaping benefits from bridging structural holes, of course you have to observe the network first, and then you can that influences your behavior. But Mark Granovetter put a slightly different focus on this phenomenon, saying that the fact that you are so much embedded into groups constrains your behavior. So those are two different views, right, on how patterns enable transactions or constrain transactions. And as we said, those are mechanistic conceptions of human action. So moving to the second application scenario, mechanistic modeling, we basically revisit a fine paper published 12 years ago on homophily in an evolving social network. The data, they take emails from 30,000 persons with a university count, who sends an email to whom as a social relations. Then they enrich this data with university records, because as we said in the beginning, the attributes are often not part of the transactions, but the transactions can be enriched, in this case by 6 attributes like gender, and the status, and so on. And finally, this is important, they have this information on who sends an email to whom over a period of 270 days. And the pattern that they find is that persons in short network distance D, so here we have network distance D, persons at a short distance, in this case, direct neighbors, have more attributes in common. So almost 3 if you're direct neighbor, than if you have, at a distance of 4, network distance of 4, they have an average of 2 attributes in common. This is a pattern that they set out to explain mechanistically. And the research questions are really, do persons choose the relations to similar others, even though they could do differently? This would be what is called choice homophily, they choose the relations. And the other, like the top-down mechanism would be, do persons choose relations to similar others because they have no other choice? This would be induced homophily because the structure, the pattern, does not give them even the choice to choose something else. And the results that they find, first, there's evidence for choice homophily, or the bottom-up way that transactions shape patterns, because the more similar two persons are, the more likely they are to send a mail on the next day. The more similar, the more attributes they have in common, the more they send in a message to that person. But they also find evidence of induced homophily, or of an effect of structure of the network, because the effect is weaker. The effect we've talked about in the slide before, the effect is weaker the larger the network distance. So network structure has an effect, and the effect even vanishes when persons share a focus. So if people have, are in the same class, this is a university setting, then there's nothing like people choosing people with similar attributes in a more likely way. So in summary, their finding is that network proximity and attribute similarity converge as distant but similar persons are drawn together, facilitated by shared activities. So this is homophily as a feedback mechanism, because you have both emergence and downward causation both going together in a mechanism. So to conclude, digital behavioral data offers fresh research opportunities because, for one, we have the opportunity to combine social relations and the content of these relations, now relatively easy to get this information, this data. We can enrich transactions by attributes and attitudes, and we have this timestamp, right? So we can do highly dynamic observations also at scale. At scale meaning that we can do this for large systems if we have the skills and the technical, the hardware to do that. So to close, I want to talk about a few challenges. One is data management. Of course, there's a need to handle this data, and I think this will be becoming more and more important, handling not just a click software, but like maybe a programming language. Of course, not everybody will want to do that, but it will become more frequent to do this in social science. There are, of course, issues regarding data quality, validity. Nodes in Twitter can be bots. You have measurement and representation errors. And if you're interested, there's two colleagues of mine have already done a talk on data quality. There are reproducibility issues regarding data, because very often it's problematic to share this data. It's produced by digital platform companies that are sometimes don't want to share this data, and therefore code sharing is important, so people can reproduce things or replicate things or change things. It is important to be reflexive on this data that we have. What is its mode of generation? It is important to know that those systems are not, this data is often not produced for a research purpose, but to make money, basically, right? So there is an infrastructure aspect to data creation. We have two talks, if you're interested, by two colleagues or three colleagues of mine. And finally, theory is important. There's much more data-driven work, of course, in computational social science, but theory, is so rich, concepts, such a rich set of concepts like functions, fields, systems, mechanisms, things even beyond the things we have talked about, that all have their right and can serve to create a better understanding of what is going on in this field, and that can also serve as a language, particularly the more general theories, as a language to help social scientists and computer scientists and physicists and all those people who are working in computational social scientists to talk about the same thing and to have a common language. And with this, thank you very much for your interest and your attention, and I'm very happy to discuss this with you. Thank you.